Hola, hi, this is Al, your statistics and probability instructor. Let's get to work. In this video, we will talk about some results that are going to help us find expected values more quickly and conveniently. Before we start talking about these new results, theorems, allow me to remind you about an old result, one that you have seen before. Okay? It's theorem 3.2 from our textbook, right? And we used it in another video to find the variance of a random variable. Okay? And in summary, what this theorem is telling us is that the expected value of a transformation of a function of the random variable y can be found from the probability distribution. And if we are talking about a discrete random variable, this guy is also known as the probability mass function. Anyway, you can find this expected value of this transformation g of y using the probability distribution of the original random variable y and just multiplying the probability mass function of that original random variable y by the transformation for each of those values of y, and then you add them all up. Okay? So anyway, this theorem is going to be really useful. Just as it was useful to find the variance, it will be useful to find other expected values that you might encounter later in the course. Okay? So, first result. I think it's here, slide 48. Let's see. Yeah, that's the one we want to discuss and show. Okay, so theorem 3.3. Take a look at it. Right, we have a discrete random variable with corresponding probability distribution or probability mass function p of y, and c is a constant. What this theorem is telling us is that if you want the expected value of a constant, well, the expected value of a constant is the constant itself. Let's show that. Okay, theorem 3.3. First result. First result. Theorem 3.3. Expected value of c times y equals c, where c is a constant. Proof. Okay, so the proof will be surprisingly simple. Okay, so let me just say this. By theorem 3.2, the expected value of g of y equals the sum of g of y times probability that the random variable y assumes that particular value, right? And this is done for all y's. Okay? Okay. So this is for any transformation g of y, right? So let our transformation be this. G of y equals a constant. Okay? So in that case, the expected value of c, just using this, if g of y is c, then I just plug in here instead of g of y, have a c, right? But now note that that c, that constant, is a common factor, so I could pull it out. So let me copy and paste this, and I'm just going to pull out that constant, right? I get to do that. Now note that the probability that y equals y, if you do the sum over all possible values of y, this is supposed to be a legit probability distribution. So the sum of these probabilities for all possible values of y is going to be 1. So let me just say that. Note that this is 1. And again, because we're doing this for all possible values of y. Okay? So what we have here is c times 1, which is c, which is what we wanted to show. And we're done, right? Very simple. We just applied theorem 3.2. Bottom line, expected, here, expected value of a constant is the constant itself. Okay, that's what we wanted to show. Expected value of a constant, the constant itself. And you know, it wasn't that hard. The proof is just an application of theorem 3.2. G of y, in this case, is a very simple transformation. We're sending all possible values of the random variable y to a single point, a constant, right? That's it. And we just used the properties of probability distributions. Okay, one of the properties. Okay, good. First theorem done. Okay, first result. Okay, next result. In this case, it's similar to what we just did. In this case, what we have is, if you have a constant that is multiplying a generic transformation of y, then if you want the expected value, it turns out that you can pull out that constant. Expected value of c times g of y being a generic transformation, equals c, that constant, times the expected value of g of y. Okay? Okay, so the proof is going to be easy. Just apply theorem 3.2 again. Make sense? So second result, or second theorem, expected value of a constant times a generic transformation of random variable y equals c times expected value of that generic transformation of our random variable y, where that c is just a constant. Okay, proof. Again, by theorem 3.2 we know this, right? And then in this case our transformation, let me call it let me change the notation here so we don't have any confusion. Let me call it an h function, right? C times that function h of y. The expected value of c times h of y is going to be c times expected value of that function h of y. Okay, so if we use that theorem, what we're going to be doing is just, hey, let your g of y, your transformation, be a constant times that function h of y. Then we just substitute and we're going to have, instead of g of y, we're going to have c times h of y, and instead of having g of y, we're going to have c times h of y times the probability distribution. We have that product and we are adding up those products for all possible values of y. And yeah, let me be super specific about that here, right? Let me change that one like this, all y's. I just want to be very clear about that. And then, well, this is a constant, so we get to pull it out. Right? But then, when you look at that, you go, well, that's the same as c times this, and that happens to be the expected value of h of y. So we are done. Bottom line, what I want you to remember is that if you want the expected value of a constant times a transformation of y, then that is going to be the same as the constant times the expected value of that transformation you are interested in. Make sense? Okay, so easy. we are done with that second result. Let me show you another one that is going to be useful. Okay, take a look at it. Make sense? Okay, so basically what we're saying here is this: now you are interested in a sum of transformations of your original random variable y. Okay, and then you want to compute the expected value of a sum, right? Well, it turns out what this theorem is telling you is this: if you're interested in the expected value of a sum of transformations, that is the same as the expected, that is the same as the sum of expected values. Make sense? Okay? Okay. So, what we're going to be doing is we're going to be showing theorem 3.5 for the case when k equals 2, when you have only two terms, right? But something similar can be done if you have more terms, if you have k terms like we have in this sum. Okay? And if you remember what you have done in other courses like Math 102, since this property has to do with the natural numbers, right? We have k terms here. If you show something for 2, you are basically done if you do it by induction, right? Okay, anyway, we're going to be showing this in the case of 2, and you'll see. So theorem 3.5, that's our next result, third result or theorem, which is important. What we have is we would like to show that the expected value of the expected value of g of 1, well, g1 of y plus g2 of y equals the expected value of just g1 of y plus the expected value of g2 of y. And again, basically what we're saying is the expected value of a sum is the sum of expected values. Make sense? Proof. So, expected value of this. By theorem 3.2, this is just another function, right? This would be a g star of y, meaning it's a transformation that is a sum of two individual transformations. So let me just say by theorem 3.2, the same that we have been using, this is just going to be what? The summation for all y's, possible values of y, of this guy, this ugly guy. Times the original probability distribution of our random variable y, right? Okay. Now we could expand this. It would be this guy g1 of y times this plus g2 of y times this. So let me just say that. Guys agree? Yeah? Okay. But this is the same as doing this in two parts. You first do the sum for these plus the sum of these products. Okay? So that's just doing algebra. We have this and then we have that sum for those guys. All values of y. You guys agree that this is the same as this? We're just expanding that. But this, take a look at this. This is the expected, well, this is g1 of y times the probability distribution of y. That is just, you know, the expected value of g1 of y. And this guy here, same thing. That's going to be the expected value of g2 of y. Make sense? And that's exactly what we wanted to show. Expected value of a sum of expected values. Okay, summary. So today we have talked about 3 new theorems. Let's recall what they said. Theorem number 1, or result number 1. Expected value of a constant equals the constant itself. Okay? Okay. Result number 2. Theorem that says, hey, if you want to find the expected value of c times h of y, or g of y, a transformation of your random variable y, what you get to do is this. You get to pull out that constant, right? So the expected value of a constant times a transformation of your random variable y equals the constant times the expected value of your transformation. Okay? Okay. Third result. In plain English, if you're interested in the expected value of a sum, that equals the sum of expected values. Okay? Finally, let me just say this, that if we combine these results, we will realize that if we were talking to one of our mathematician friends, we could tell them, hey, guess what? The expected value is linear. Okay, that's it for now. Please take care and keep working hard. See you next time. Bye.